AP Calc class, we're going to take a look at section 5.3, which is going to be solving some differential equations again, concentrating more on separating the variables. So these will be a little more extensive as far as steps needed to get the x's and dx on one side and then y terms and dy on the other side. They do give us a few examples to start off with the original differential equation and then what it's going to look like after the variables have been separated. And one of the key things that I always tell students is that the dx that's in the denominator can't, the dy or dx can't be in a denominator, so the dx would have to get multiplied. Now, before you would do that, if there's another term being added or subtracted, we would want to subtract the x squared to the right side of the equation, and then we could multiply by the dx, which is kind of what's happened here to separate those. I won't talk through each of these. We'll just give some examples, or we'll go through some here. But again, so like a key thing is, you have to multiply by that dx in the denominator. Now, if they've given you the derivative form where it's y prime rather than dy dx, you'll want to rewrite that as a dy over dx to get that one started. Okay, so for example 1, find the general solution. So the general solution would be, separating the variables, integrating, and then we'll have our constant of integration of our plus c on one side of the equation. Particular solution is plugging in some initial conditions and then solving for that c value. All right, so let's start this off. So I've got x squared plus 4 dy dx equals xy. Okay, so like I said, we're going to need to multiply. Excuse me, sorry about that. We're going to need to multiply by the dx over to the other side. I think I would do that as a first step. And I might not show every single step that I do here, but let's talk through them. So if we multiply dx to the other side, we'll end up having to divide by the x squared plus 4, because this is all being multiplied here. And then we would divide this y over to the other side. So on the left side of the equation, I'm going to leave dy there, but I would have divided by y. So I'll have 1 over y dy. There's 1 over y dy on the left side. And then on the right side, I'm going to multiply the dx over there, and then I'm going to divide by the x squared plus 4, which is going to leave me with x over x squared plus 4, and then I'll have the dx on this side. So there's my separated equation. Now that the variables are separated, I can integrate each side. Okay, so I'm going to take the antiderivative of each side. And the left side of the equation, we've seen this one a lot. That's just going to be our ln of absolute value of y on that side. And on the right side, this is going to be a little more involved. I think we'll have to use, I'm going to write out a u substitution for this, since I can see the degree of the numerator is 1 less than the denominator, and I only have the one term up there. I think if I let u equal x squared plus 4, then I can have du equal to 2x dx, and so I could say 1/2 du equals x dx. So if I rewrite this in terms of u, I would have 1/2 the integral of, and then I would just have 1 over u du, which means when I integrate that, I would have 1/2 ln u plus c, and substituting back in for my u value, 1/2 ln of x squared plus 4 plus c. X squared plus 4, it really can't be negative because you're squaring and then you're adding 4, so I'm not going to put it in absolute values. And then I've got my plus c. And you only have to put the plus c on one side of the equation. I would typically put it on the side with, a lot of times if we can write this as an explicit equation, y equals something in terms of x, it's more useful to have the c on the side with the x term, so I'm going to put it over there. Okay, now to simplify this a little bit more, properties of logarithms, if I have a coefficient in front of a log, a natural log, or a common log, whatever, remember there's a property that says I can actually take that, that coefficient right here, and I can move it as an exponent on the term that I'm taking the log of, and that's going to maybe help us a little bit here. So ln of y equals, and so if I have something to a 1/2 power, that's the same as a square root of that, and so I'll have ln of square root of x squared plus 4. So it'd be, the x squared plus 4 to the 1/2 power, which is the same as this. Okay, and now I can write this, because you know, I have ln of something here. Really, I'm just going to kind of show how I would do this. I would write this as an in exponential form, you know, so I could do, this is a base e, so y equals, you know, e to the ln of square root x squared plus 4 plus c. And we know that like an e and an l, those are inverse operations, so that's basically cancels and leaves me with the square root of x squared plus 4. But then also this plus c, remember when we did this work before too, I'm just going to write this one more time, ln of square root of x squared plus 4, and then it would be the same as times e to the c, right? We kind of did this when we were setting up our, you know, some of our exponential growth and decay equations, and then this term right here, e to the c, that's still a constant, so we could just call that c times e, or so this e to the c could go and change into, this can change into a big C, so I can just call it y equals c e, and then to the ln, so this part here that cancels, I'm just going to change that back into square root of x squared plus 4, and then I would just leave it probably in that form. Okay, now this is my general solution. This is what I would call a general solution. Okay, and now I need to also find the particular solution. So to get the particular solution, I'm going to plug in these initial conditions that I was given. So y equals 2 and x equals -3. So y equals 2, x equals -3. So that's going to give me a square root of 13. So I'll have c equals, let's just write it like this. So the square root of 13 times 3, square root of 13 times c, dividing that out, c would equal 2 divided by square root of 13. So if I go back and substitute that in right here, I'm going to have 2 over root 13 square root of x squared plus 4. And that would be this would be the particular solution. Okay, so there's a general solution here and a particular solution, one of each. So there's one example of separating variables, solving your differential equation. All right, couple more examples, just little different looks at some of these equations. Okay, so for example 2, again, we're going to want to separate these variables out. You can already see that the dy and dx are already kind of separated. It's not dy over dx. So we just need to move these terms around. I think probably what I'd do first is take this x, y, dx, and I'm going to move that over to the right side of the equation. And I'll have negative x, y, dx. And then for the other part, give me 1 second. I got some kids at the door here. Okay, I'll have to help you a little later. I'm making a video.
You know what period you want to whenever you're available, period? I'm available till like 11:45 or 11:53.
Yeah, you want to stop back in like 15 minutes.
Okay.
Okay. So, sorry about that. Okay, so what we want to do now, since I have, oh, I forgot to leave the dy on this side, so dy was there. Okay, so I have the y's and dy's here. I have some x's and dx's here, but I have to move this y by division over to this side, and probably divide this e to the negative x squared over to this side. So on the left side, I will have y squared minus 1 over y. I'd have dy after that. And on the right side, I have negative x dx, so I divided that y, so that's not there. And I'm dividing by e to the negative x squared. Okay. Now I think I'm going to rewrite this a little bit before I integrate. So these terms, I've got y squared over y and then negative 1 over y. So y squared over y is just y, and then I've got 1 over y. And on the right side, I have got e to the, now this, because it has a negative exponent, negative x squared, I can move that up to the numerator. I think that's what I'm going to do. So I'll move it up to the numerator and make it a positive exponent of x squared. So I'll have negative x, and then I'll move that e up, so it's going to be e to the positive x squared, and then dx, like this. Okay. Now I think I'm ready to do antiderivative of each side here now. Okay, so I'm going to work that out up here. So with this left side of the equation, antiderivative of y is just going to be 1/2 y squared. The antiderivative of 1 over y, that one's ln of y, so minus ln of y. And on the right side of the equation, so I think for this part, again, I'm probably going to do a u substitution. If I let u equal that x squared, then the du would just be a 2x, which is similar to what I have here, so I should be able to make that work. So if I let, for this part, u equal x squared, then du would equal 2x dx, and 1/2 du would equal to x dx. Okay, so on the right side, I can rewrite this as, I'll pull that negative out, and I'll pull the 1/2 out, and then I would just have e to the u du. Okay, so 1/2 integral of e to the u du. Okay, and that should be pretty easy to integrate. Okay, antiderivative of e to the u is just e to the u, so that's pretty straightforward. I'm just going to recopy this. 1/2 y squared minus ln of y equals 1/2 e to the u plus c. Now, for that e to the u, I'm going to plug back in x squared. I think I'll just do that in this step so I don't have to recopy it all. So u is x squared. Oh, sorry, this should have had a negative with it because there was a negative in front of that, so this should be negative right there as well. Okay, so some of these, in the last one we solved for y, but this one's not going to be real easy to solve for y because it's got 1/2 y squared, and then you got ln of y. You can't really get those together, so I would just leave it as a, it's not an explicit form of our equation, but it's still a correct equation that's been solved. Okay, but we do need to also plug in now our initial conditions and then solve for the c. Okay, so we'll have 1/2, and our y value is 1, ln of 1, and then our x is 0, so I've got negative 1/2 times e to the 0 plus c. Okay, so 1/2 times 1 squared is 1/2. ln of 1 is 0, and then negative 1/2 times e to the 0 is 1, so that's just negative 1/2 plus c, and I'll add the 1/2 to the 1, so I get c equals 1, right? So my particular solution then, I know that c is 1, so I'm just going to go right back up to this step right here. C was 1, so I can say plus 1. That would be my particular solution for this equation. Okay. And the last example says find the equation of the curve that passes through 1, 3 and has a slope given here. Now when they state this, it has a slope of, that means it's a derivative, right? It's the derivative of some function. It's in terms of x and y. So derivative of y with respect to x, which is your slope, slope finder, would be y over x squared. So that's kind of what they're telling us here. That's our differential equation. So let's separate the variables, multiply the dx over to this side, and divide by the y or multiply by 1 over y. So how that is going to separate out, I'll have 1 over y dy on the left side, and I will have multiplied the dx over here, so I'll have 1 over x squared dx. Okay, and now integrating the left side, that's just going to be ln of y like we've seen before. And on the right side, though, 1 over x squared, that one's just a power rule. You can think of that as x to the negative 2. And when you integrate that, you're just going to add 1 to the exponent and divide by that. So adding 1 is negative 1. And so if I divide, it'll be x to the negative 1 divided by negative 1 would be, negative 1 over x is what we get for that, right? So this would be negative 1 over x plus c. I'm going to put the plus c on the right side of this equation. And, all right, so that's pretty much simplified there. Let's change it. This one we can solve for e. We can put it as in exponential form and solve it for e. So I would rewrite this as y equals e to the negative 1 over x plus c power. Which again, you know, I can think of that as negative 1 over x times e to the c, and that c, you know, e to the c is a constant again, so I can put that in front, c e to the negative 1 over x, like that. Let's see here, I feel like I've missed, okay, so I still need to plug in my 1, 3, and I need to figure out what that's going to be for my c, then I can solve for that. Okay, so if I put in 1 for x and 3 for y, 1 for x, so that's just going to be e to the negative 1, like that. And so that means that'd be like 1 over e. So I'd multiply by e to cancel and move it over here. So I'd have 3e is what my c value is then. And so when I come back here and write my particular solution, I'd have 3e times e to the negative 1 over x. Now that's e to the first, so I have to add these exponents. 1 plus, you know, negative 1 over x, which should just be 3e to the 1 minus 1 over x, like that. And that's probably fine. You might see this, you know, as a common denominator, like 1 you could call x over x minus 1 over x, so you might see it written as x minus 1 over x. If you think of, you know, 1 with a denominator of x, it would be x over x, so it would look like this. Either of these is probably fine. Okay, so that is it. That's some solving differential equations where we separate